I'm so pleased this morning to introduce our inaugural Valenta-Wiesner lecture series speaker, Dr. Mark Lautens from the University of Toronto. To summarize it, I would easily say that he's the preeminent organic chemist in our country and probably in a wider area than just Canada. Dr. Lautens grew up in Hamilton, did his BSc at Guelph, then went to the States. He did his PhD with Barry Trost in Madison, Wisconsin as an NSERC postgraduate student. Then went to Harvard and did an NSERC postdoctoral fellowship with Dave Evans, I should say the late Dave Evans. And then came to the University of Toronto to launch an extremely successful career in synthetic organic chemistry, methodology, catalysis, and really has demonstrated a mastery of how to use metals in catalyzing not just single reactions, but cascades of reactions and linking reaction processes together in an absolutely remarkable way. Now, if you want to know what kind of awards can an organic chemistry professor in Canada receive, you just have to look at his CV or his Wikipedia page or the UNB News. The list of awards is huge and very important awards. I mean, he's an officer of the Order of Canada. He was a Stacey Fellow. He obtained a Killam Fellowship. He obtained the Arthur C. Cope Award from the States. What else? He was a Sloan Fellow, a Lilly grantee. He was also a past chair, was a medicinal research chair with Merck, and it goes on and on and on. He has trained hundreds of scientists in his career, many of whom are in academia, others in industry. His publication record needs a little bit more work, though. I think it's just under 500 papers in his career. One quick word on another side. He's a strong proponent of supporting science in Canada. And so he's a strong advocate of increasing funding in Canada for science and improving the overall funding situation. He is also a popular individual in newspapers, in the Toronto Star, the Globe and Mail, either talking about advocacy for science or about how online learning is affecting our students. So it's my distinct pleasure in welcoming to UNB Dr. Mark Lautens for this inaugural Valenta-Wiesner lectureship. So welcome to UNB.
That's important.
You can have a pocket.
Perfect. I got a pocket here. Well, I have to begin by thanking Ghislain both for the very kind introduction and also the invitation. So I've been a professor now for 35 years, and I've never been to UNB before. So this was a fantastic opportunity for me to see. And for anybody who follows my Twitter feed, of course, I came to Atlantic Canada and found snow. So that was more or less a perfect introduction to my first visit. So thank you very much. It's also a special privilege, I think, and pleasure to be recognized with this Wiesner and Valenta lectureship. I never met Professor Wiesner, but I knew of him. I think he's really a legendary figure in terms of organic chemistry in Canada. And when I came back to Canada, or even when I was an undergraduate at Guelph, you know, there were these beacons across our country. One of them was Ghislain's father, of course, but Steve Hennessy and Pierre Delanchon, Ed Pears, Derek Clive, and on the East Coast were Wiesner and Valenta. And so to be recognized in this way, I think is very powerful and very nice, and it's a real pleasure to be here. So one of the things I thought I would do, even though it's in there, is I thought I would just mention a few things about each of them in some ways. It's not true I'm at near 500. I think I'm just a little over 400. But now I can tell my students, they're saying 500. I think we better work harder. We don't want to let them down. But this is a lot of students trained. When I think about it, especially back in the day, he was very big in structural elucidation, but also natural products. And indeed, he had the Order of Canada back in 1975, which was early days of the order. Although I won't talk about it today, we're actually working on a total synthesis of aconitine. I think I may have to live to 100 to reach it, but it's an incredibly challenging molecule, and to think that people were studying this all those years ago is absolutely phenomenal to me. Denny Valenta, I don't know that I actually ever met him, but a bit of information about him and his association with UNB, and I think he seems to have been especially influential in teaching and in education, joined with research, and many people, including some around here, have affiliation directly and indirectly with Valenta and with Wiesner. So, what am I going to talk about today? I'm going to talk about one thing for sure, and I may talk about something else depending on how slow or fast I talk. What I'll talk about for sure is chemistry, but at the end, I was at UBC a couple of weeks ago. The students invited me, and they asked me to talk about advocacy. So I threw in some slides about advocacy that are kind of at the end. So if you're interested at all in advocacy and what that means to an old geezer like me, by all means, we'll talk about it at the end. So what do we really care about as organic chemists? We're interested in what we would call synthetic efficiency. And what do we mean by that? So I've given 3 examples on this slide that will talk about our idea of what efficiency means, but it's other people's work. So here's some work by a Spanish chemist, Antonio Echevarren. And this is a kind of efficiency which I would call isomerization reaction. So all the atoms in the starting material appear in the product. There's no waste of atoms. Trost calls this atom economy. So all these atoms here are in here, but only this is an acyclic and easily made by standard acid-base chemistry, and this is a complex cycle that is not so readily accessible. So he used a gold catalyst to isomerize this ene-ine into a diene. Here's another strategy which I'll touch on today, which is domino chemistry, how to mix a bunch of things together. So this is work by Matthias Beller in Germany. He's at one of the big institutes in Rostock. And what he did was take 2 metals, rhodium and iridium, and 1 ligand. This is a water-soluble phosphine. And he put together 4 components, a double bond, an amine, ammonia I should say, and then carbon monoxide and hydrogen, and he did a rhodium reaction, in this case adding HCOH, and a reductive amination. So from these simple building blocks, he built something complicated. Now, that's not very complicated compared to the molecules I showed that Wiesner came up with, but these, on the other hand, are pretty much the simplest building blocks that chemists have. So we built a lot from really quite a little. And what we did was we combined the use of 2 different metals, and that's what I'll talk about towards the end of the scientific part. And then the last thing I'll tell you about is some work from Jin Kuan Yu. He's based in Scripps in the United States. And his theme, and one of our themes, is how do you get things that typically you think are unreactive to be reactive? And the most unreactive things we think about typically are carbon-hydrogen bonds. Unless they're adjacent to a carbonyl group, so you can do sort of acid-base chemistry, we generally think remote CH bonds are inert, except maybe to radical halogenation, which you learn in first year. But what Jin Kuan Yu found was that you could treat it with a palladium catalyst and, for instance, iodobenzene, and all of a sudden you could replace a CH bond by a CC bond and introduce a bigger, more interesting group. So those all represent a kind of efficiency. You either get an unreactive bond, you do a domino cascade, which is very reminiscent of biology, except this is metal-driven biology, or you just rearrange the atoms into something way more complicated. That's a little bit like biosynthesis, where you put things together and then you typically get a cascade. So that's the background. So I'm going to talk really about these two things, palladium and nickel, and multi-metal catalysis. I had a third topic, which is why there's a hole there, but that got replaced by advocacy, I hope, at the end. Okay, so let's start off with palladium and nickel. So let's go back to some chemistry done by a British chemist, Ron Grigg. And what he did was he took, for instance, simple molecules like an iodobenzene linked together to a double bond, and he treated them with palladium, and we get insertion into that bond and addition to the second bond, and now we have this more complex cycle. Now, depending on what R is, many different things are possible. So what he did was trap the palladium with a nucleophile. So what we've done is essentially build a carbon-carbon and a carbon nucleophile bond. So we built two bonds from something very simple. We showed that if the R group was an aromatic ring, that all of a sudden we could do a CH activation. That's like what I told you Jin Kuan Yu did. And normally we don't think of ortho-CH bonds as being reactive, but they can be. And then we can either make a strained cyclobutane, or we can insert another double bond, in this case an alkyne, and we get these spirocyclic compounds. So we published on that already. But what I want to focus on today maybe is what happens when there's nothing in there, when there's no group to trap, and when R is not an aromatic group. Then you can do a reaction that reduces the palladium, regenerates it, and makes a carbon-iodine bond. Now that seems so simple. This is an isomerization, right? All the atoms here appear here. So it's extremely simple, and yet it wasn't known. So that's what I want to tell you about. So first, a little step back. In 2001, John Hartwig at Berkeley did this mechanistic study. This is, let's call it a classic organometallic mechanistic study that had zero synthetic utility. Okay, why do I say that? Because iodo-toluene is cheap, and this stuff, especially with tri-T-butylphosphine, is expensive. So this is the wrong direction, right? We don't usually start with something expensive and make something cheap. That's not a good way to become rich. What he found, though, was really important intellectually, which is that a bulky phosphine ligand helped to promote the reverse reaction. So this reaction, going from right to left, is as old as organometallic chemistry, but the right-hand reaction was essentially not known. So mechanistically, he showed this group being present facilitated the reaction to the right, and a bulky phosphine facilitated the reaction to the right. That was the learning experience that a PhD student of mine, now professor at Ottawa, Steve Newman, used to make something useful. So this is not useful, but the intellectual observation is very useful. And what Steve showed, which turned out to be useful, was how to make brominated indoles. Now that might look like an easy compound to make. It turns out it's not, because that carbon-bromine bond is really reactive. So finding a catalyst that would let you go from right or left to right was no small feat. And Steve spent an enormous amount of time until he found this Hartwig paper. And then when he used that ligand, all of a sudden the reaction worked. Now, as is often the case in chemistry, you know, we actually submitted this to Science. It went through multiple phases and never got accepted, but it wasted about a year. And it turned out somebody else was working on the same idea, but Steve first published, so 2010 he published this. In 2011 he published that we could reversibly insert into a carbon-iodine bond and then reform it. So in this substrate up here, actually the palladium is inserting back and forth into that bromine, but it's catalytic, so it just regenerates the starting material. So it inserts, deinserts, inserts, deinserts, but that lets us isolate this. If we couple this insertion-deinsertion to a double bond, all of a sudden we get a carbohalogenation. And that paper came out in 2011, and soon thereafter the group of Tong, a few months later, found a similar observation with different ligands and conditions, but basically the same. This ligand, notice we changed from tri-T-butylphosphine to this ligand that he had invented, Hartwig had invented, called Q-phos. It also has a very bulky phosphine, but it has a ferrocene on it. Anyway, this sort of led us down a path. And there's the reaction, and here's some substrates, but there's one substrate that kind of jumps out, and it's this substrate here. This is called an oxindole. And that oxindole is very commonly found in pharmaceuticals and natural products. Here is a natural product. Here are two pharmaceutical agents, and all of them have this red oxindole component. So this became a kind of a black hole of our research, because everybody in the group started trying to make oxindoles, as you're about to see. So for better or worse, this one substrate stimulated us enormously in terms of making things. And you'll see at the very end of this, we made something useful. So here's 2011, the first paper. Now, palladium, here's the problem. Palladium is expensive. That's bad. But if you think palladium is expensive, you should think about the ligand. The ligand is usually costs more than the metal. So everybody talks about how much the metal costs, but the metal is somehow recyclable, and the ligand for sure is almost not recyclable. So this was a problem. Q-phos is expensive, palladium is expensive, and palladium Q-phos, if you buy it, is really expensive. So for years we were trying to find something other than palladium. And although it's not a story for today, it's a good story that nickel we found half by accident and half intentionally. So here's some nickel chemistry, reversible reactions. Nickel can insert into carbon cyanide bonds and then replace the carbon cyanide bond. That was discovered by Jacobson and Hiyama. And then we discovered it just here. So let me go on and show you. So Hyung Yoon, who now works at AbbVie, Austin Marchese, who just got his PhD and is about to go to Columbia. So they found that nickel diiodide, that's really cheap, and triphenylphosphine, that's about as cheap a phosphine as you can buy, together were excellent catalyst. Now, there's a few limitations that we needed a carbonyl group attached to that nitrogen, either directly or we needed the carbonyl group here and then an allyl tether. But this reaction works surprisingly well and makes the same kind of molecules but under much simpler conditions. And here's just a few examples that just show we can put substituents all over the place. If you want to be a medicinal chemist, you need to be able to make many structural variations, and that's what we set out to do. So we put substituents pretty much everywhere, on the nitrogen, on this ring, pretty much everywhere. Not all of them work equally well. If this group gets really big, then the yields drop a little bit, but generally speaking, pretty good. Now, one of the things I didn't tell you was in this process, we go from an achiral molecule to a chiral molecule. So if you make a chiral molecule, you want to make a single enantiomer, right? One of the two hands. That's sometimes easy and sometimes not easy. With palladium, we screened, we collaborated with Merck, we screened 250 ligands in their library at their company. We found two observations. We could get a great yield and a lousy EE. Or we could get a great EE and a lousy yield. So we could never get that sweet spot of a good chemical yield and a good enantiomeric excess or ratio. Later, 10 years later, a group in China invented a new ligand, and that ligand turned out to be excellent, but at the time there was none. So we looked at nickel, and again, this is a beautiful story of accidents and how accidents happen. It turned out, so BINAP is a chiral ligand, and BINAP-O is when it gets a little bit oxidized, so it's an old bottle. And I had two students. One worked with R, and one worked with S. The one who worked with R said it works. The one who worked with S said it fails. Well, that's impossible. They have to both work. When we looked closer, one bottle had been oxidized, and it worked. The one that was pure failed. So a lucky break that got us this observation. Now, the enantiomeric ratios were not off the charts, but they were about the best that was out there at that time. So there's all kinds of good scientific stories to be learned from this, but we'll save that for another day maybe. Anyway, during this process, we sort of said, can we flip the script? Can we, instead of having an aryl iodide with a tether and a double bond, what about if we have a styrene and a carbonyl chloride, so a carbamoyl chloride? Could we do this reaction and do any better than this enantioselectivity? So that's what we did, and that worked out beautifully. So this was a collaboration. A German student from the Glorious group joined our lab for 6 months, and Austin worked with him, and there's Frank Glorious's name there, and so there's Austin. He'll appear many times in this talk. Now, we started with a carbamoyl chloride, but we didn't get a chloride here. That final formation of the carbon-chlorine bond is really tough energetically. We've done computational work to show that that final step is really tough. So we added potassium iodide, and now it works. So we essentially swap chloride for iodide. But you can't start with the carbamoyl iodides. They're too unstable. So you need something that's cheap and easy, and it makes something complex and hard. Anyway, you can see the enantiomeric ratios now are finally good. So that was awesome. So let me tell you another story. We're going to not quite switch gears, but it's about reversibility. And here's the story. So back in 2014, there we go, 2014, Dave Petroni, who's now at Merck, discovered this is the palladium reaction. And what he said was, if we have a group already present, what diastereomer do we get? And the diastereomer he got was aryl was up and methyl was up. So we called that syn. And when Austin discovered the nickel reaction, he tried that. And much to our surprise, we got the anti. Now, we never really have understood why we got the anti, but for sure we got a different product. Now, here's what was interesting. By making 2 diastereomers from a reversible reaction, we asked ourselves, what happens if we just take the same substrate and now we use palladium but a different ligand? And it does the addition, and then it inserts into this CH bond, which I'd already mentioned to you was one of the reaction pathways. So now, from one common starting material, we had 3 products. And then Austin asked the most important question of all, which was, if we started with these 2, what would happen if we subjected them to this reaction? And that's where the surprise came. Somehow, the anti-product gave the syn tetracycle. This one is easy. The methyl and the aryl are on the same side. That should be easy. But this one, they're on the opposite side. How did it get from one side to the other? We made a proposal. The proposal was that there was a beta carbon elimination, and that's very rare. And so Austin and Bijan was our computational expert, put together to understand this reaction. And the proposal was that somehow the palladium inserts back into that carbon-iodine bond and then actually breaks this bond here to make this species. And that somehow everything is converging. So here's the experiments that we did. We took the anti, we got 45% yield. We got an X-ray to make sure we knew what we were talking about. And we also got a lot of just proto-deiodination. Then we took the open, and that gave us the same product but in higher yield and less proto-demethylation. Then we took the one that was already on the same side, the syn, and that gave us the best yield and none of this. In other words, the closer we are to the end, the better the yield, and the less of this side product. So this is the furthest from the end, this is the middle, and that's one step from the end. So it's kind of like the closer you are to the finish line, the chances of finishing are better. All right, so what's going on? We thought the palladium inserts into this carbon-iodine bond, but this cannot CH activate because this is a transfused ring, and that's too strained. So instead, the beta carbon eliminates, regenerating the double bond, and now it flips from one side of the double bond to the other, cyclizes, that makes the syn, does a CH activation, and then gives the product. So this is why, if we're at the anti, we have the longest route. If we're at the syn, we just have 2 steps. And if we're at the acyclic, we have 3 steps, or so we thought. But there's a couple of other mechanisms that could take us from here to here. One is the palladium is jumping from one methyl to the other, or the other is what happens if this center is actually epimerizing. So we're not really seeing anything exciting at all. So we had to rule those 2 things out. So we took the one with a methyl and an ethyl, and we thought, well, if it jumps, it'll jump to the ethyl in order before it cyclizes. And if that happens, either we'll get this or this. And what happened was that wasn't true. In fact, from the anti, we got a way better yield than before. Before it was only 45. All of a sudden, it was 75. And the syn was even better. It was 70 before. Now it's in the 80% range. This was published in Nature Chemistry earlier this year. None of these were observed in any case. So this tells us there is no 1,3 shift of the palladium from one methyl to the other. What about epimerization? How could we test that? We tested that by starting with an antimerically pure material. If this is an antimerically pure, then if it epimerizes, then the 2 starting enantiomers will give different products, and that wasn't the case. So this gave one enantiomer, and this gave the same enantiomer. So if this had epimerized, we'd actually get the enantiomer to that product. So the optical rotation would be the opposite. But this, whether it was open or whether it was closed, we got the same enantiomer. So there is no epimerization at that center. Same enantiomer, therefore no inversion of the quaternary center or these. So this is all out. Forget those, forget that. This is our route. This was not a synthetic paper, I must tell you. This was a mechanistic paper, but we did set out to show that it was a little bit general. I mean, it's not really, nobody's going to make any molecules, I think, by this, but conceptually it's important. So here's some examples. With methyl, under our best conditions, 58% yield, 45 under our original conditions. But if we swap the methyl to an ethyl, the yield jumps up. If we put a halogen in there, even though halogens react with palladium, no effect. And if we put electron withdrawing group, even better. So it's a pretty general reaction in terms of our groups and substituents elsewhere. So one thing we thought was kind of fun would be what happens if we took a mess. If you took a mess and made something clean from it, that would be kind of intellectually satisfying. So I call this all roads lead to Fredericton. No matter what you start with, you end up with the same product. So if you take a 1-to-1-to-1 mixture of 3 things, you get a single product out at the end. So that tells you everything is reversing until it finally gets to the very end of the road. Okay, here's our very latest stuff in this field. And it was driven by this paper from Vladimir Gevorgian. He put palladium with blue light, blue LEDs. Now, this is a very emerging field, LED chemistry, photochemistry. I mean, photochemistry has been going on since Italians did it in the 1800s. But now it's very popular because of LEDs. So for instance, if you insert the palladium and shine light, you get a radical. The radical abstracts a hydrogen. Now you make a new radical. That radical cyclizes, and then it traps again the iodide. So that was what Gevorgian showed. We wondered, could we start with our starting materials and get our products using LEDs? And now we could use, you'll see the ligand in a moment, but these are now at room temperature. So I didn't say this before, but before it was 100 to 120, and now all of a sudden it's working at room temperature. So this is the examples. This just appeared in JCS at the very about a month ago, and there's Austin has again made his appearance. And here's some substrates. Now, why do I put up these substrates? These are all substrates that were lousy in our previous chemistry. a free NH2, a free carboxylic acid, a free phenol, pyridines, all were messing up those earlier versions of our palladium and nickel reactions. So by going to low temperature and light, we could fix a problem that was kind of long-standing in this chemistry. You can see, though, 2010 to 2022, so we're not very fast at solving problems, it seems. So what did we learn from this study? So first we did some mechanistic study. We took this vinyl deuterium. So the reason for putting that deuterium in there is we wanted to know if this was a 2-electron or a 1-electron process. And what we thought was, if we have a deuterium there, when the palladium cyclizes onto here and creates a stereocenter here, it's also going to create a stereocenter there because we got a deuterium, a hydrogen, and a metal. So that's 4 different things on there. So that's diastereomers. So if it's a 2-electron process, we'll make diastereomers, and the deuterium will stay put. So it'll be 65 to 0 because it's 65% deuterium incorporation. On the other hand, if it's a radical reaction, it'll make a radical here, and that radical will be epimerizable, so we'll get a 1-to-1 mixture. That was our thinking. So there's the radical, there's the palladium. What happened? 1-to-1. That tells us something here. It tells us that at some point we have a radical. It doesn't tell us we have a radical mechanism. It tells us we have a radical intermediate. So we spent the next bit of time trying to figure out if we could prove about radical starting point from here or radical intermediate here. So it suggests this, but it doesn't say how it got to that. That was the key. So here's what we did. We took the product from our palladium original reaction, which is palladium 2, and it's basically 58 to 7, which adds to 65. So it's a complete selectivity which deteriorates a bit over time. So it starts at 8.5 to 1. We use our conditions with no light, it stays, nothing happens. We try our light with ligand, but no palladium, nothing happens. It's always 58, 59, whatever. We try with everything here and light, but no palladium, nothing happens. So palladium with no light, nothing. This ligand with light, nothing. Phosphine with light, nothing. If we take with palladium and light, immediately it equilibrates. So that tells us this product with palladium and light generates a radical. And that radical then gives us 1-to-1 diastereoselectivity. So that tells us the end of the mechanism. It doesn't tell us the beginning. Next, we tried to figure out more. So we tried to make the complex with this ligand. That's that ligand I mentioned before, DPE-phos. It's a bridging ligand. We tried to make it. We couldn't isolate it, but we could detect it by mass spec. And then we shone a light, and it made the iodide. That was important because it tells us if we have a carbon-palladium-iodine bond, it will reductively form the carbon-iodine. We did better with this complex. This complex is the triphenylphosphine one. If we don't shine LEDs, this never will reductively eliminate. And that takes us back to the very first slide I showed you, because what I said was, unless you have those bulky phosphines that Hartwig had invented, this step never happens. And that we don't have those fancy ligands, we just got these ones. So nothing happens. But if we take those same conditions and shine light, it immediately happens. So what does that tell us? It tells us that the reductive elimination requires not the choice of phosphine, but the presence of light. So this is the end of the mechanism, right? The end of the mechanism is we form this iodide from a 1-electron type reduction using blue light, and it's reversible because we made the product and we made the intermediate and we showed there going back and forth. So the end of the mechanism is good. The beginning of the mechanism, it's known palladium can interact with blue light. It could make a radical by interacting with this aryl iodide, or it could do an oxidative addition. That's possible. This can cyclize to make a radical, and that radical is reversible. That's the end. But we also know this can cyclize because we made that complex, and the key finding was this. This and this interconvert. So we showed the product interconverts with an intermediate, and the palladium complex interconverts with that same intermediate. What we don't know is which of these actually is happening, or whether both are happening. But what we know is the conditions under which we formed these intermediates are much milder than what we formed in the days gone by. Okay, let me just quickly go through this next little bit. This is the work started by Christine Lee, who's now a professor at York University. She was doing carbohalogenation, but making a special class of oxindoles called methylene oxindoles. These are really important, and she developed two catalysts, palladium-0, which gave trans addition, and palladium-2, which gave cis addition. So there's her papers right there from 2015 and 2016, and this was based on some work she found. The second of them was based on some work from a group from 2007. So this is what Christine made. These are her conditions, and she showed that we could displace this vinyl chloride with an amine, a thiol, or a palladium catalyst. So this gave us access what turned out to be a bunch of really interesting molecules. So let me now jump forward. Christine has graduated. Jose Rodriguez comes along, and he says, she used palladium, I'm going to use nickel. That's going to follow just exactly the same thing that Austin did. I'm going to replace that expensive palladium stuff with cheap nickel. So he comes to me, look at this. I got this to work. Carbomoyl chloride, alkyne with these conditions. But he's a really smart student. And because he's a really smart student, he does all the control experiments. So there's the nickel catalyst. There's the bipyridine. He puts everything together. Oops, the control experiments say we don't need nickel and we don't need the ligand. Oops. So we're no longer metal catalysis chemists anymore. We have changed fields midstream. But that's okay. Nobody's complaining. He showed that the solvent mattered a lot in these cases. And ultimately, if he replaced trifluoroethanol with hexafluoroisopropanol, he got this reaction to happen. So this is like Christine's reaction, only it worked with alkyl here, and it gave the trans product. And we think, but we don't really know, that maybe one of these mechanisms is involved. But here's what's really cool. This reaction works super well with no catalyst except for hexafluoroisopropanol, 8 equivalents in toluene at 100. And I'll just throw a few examples up here because I want to get to the punchline. Well, there's two punchlines. One is if you take away this aromatic group, it adds cis for reasons we simply do not understand. So the mechanism kind of changes in some way. We're not sure if it's that the chloride addition is reversible or something else. But here's the real punchline. I was on the phone to one of my retired colleagues, an elderly colleague, who was not in great condition, great health. And he said to me, I'm taking this new drug, and it's really expensive. And, you know, if you're an organic chemist, as soon as somebody names something, you Google it to find out what the structure is, right? That gives you your card-carrying organic chemistry credentials, that you immediately want to know the structure when somebody says a word. He said, I'm taking this drug right here. And for the first time in 35 years, I could say to somebody, I think we can make that. I think we invented something last week that we can make that drug. So this was a happy moment, I have to say, for me, though we're not supplying him with this drug. I'll just preface my remarks with that comment. So here's the drug, and I said, you know, we just developed a method to make these methylene oxindoles. So we used Jose's method, ably accompanied by an undergraduate, a first-year student, and a senior graduate student. We make this compound in just a couple of steps, right? It's made from the aniline and then a Sonogashira coupling. So a couple or 3 steps, we can make that. And then here's our aniline, which again comes from a simple acylation of simple molecule. And we use the hexafluoroisopropanol. TFA clips off the protecting group, and A does the addition elimination. And so this is used to treat pulmonary fibrosis and other COPD and so on for people who probably smoked too much in their life. All of a sudden we could access this compound. So we were really happy, I'll be frank. Okay, how much time do I have? My watch says 1:15, but that thing says like 2 minutes to 1. Okay, well, I have 15 minutes? 15 minutes, I better speed it up. Okay, we wanted to imitate nature. So nature puts everything together. It has a cell, it has a system, all the catalysts are present. The catalysts are a whole bunch of enzyme catalysts, biocatalysts, and somehow they all can be together. Now, the difference with nature and us, or chemists, is if you're doing chemistry methodology like me, you want your method to work on every substrate, and nature would like it to typically work on one substrate. So nature likes it to work very well on one thing, and we want it to work very well on everything. That's a bit of an incompatibility, but we had this idea based on the work that I showed you before. So here's how organic chemists have worked from time immemorial, and every graduate student will tell you, this part's pretty fun and this part's not so fun. And if you have to repeat that 10 times for a synthesis, this is the part you really don't like. So we asked ourselves, what would happen if we replaced all those purifications with one purification? That we put everything in the flask with all the catalysts and got the product. That would be a way to mimic nature, but shorten the less pleasant part. So this is not so easy, even though the way I'll describe it may make it sound that way. Because when you put things together, you have to think about the conditions. Like you couldn't put an acid and a base together. That would just be called a neutralization. You can't have something that's sensitive to water with something that needs to be done in water. So it's not, this is not the panacea that you may get the impression after I've told you this story. But the story begins around the same time as Steve Newman's story. Jane Panteleev and Lei Zhang, who I don't have a picture of, he's a big dancer, so I could have put up one of his dancing pictures. He's really a terrific ballroom dancer. They were doing two reactions. We had this collaboration with Merck. We were trying to make these molecules. And the first step they wanted to do was a rhodium step, and the second step was a palladium step. And here's the thing they told me that made the switch go off. Everything that worked with palladium failed with rhodium. Everything that worked with rhodium failed with palladium. We now had catalysts that looked like they did only work with their certain ligands. So we put them together. Rhodium did the first addition of this aryl boronic acid to an alkyne, and then palladium did a Buchwald-Hartwig CN coupling. So we said, can we put them together? And the answer turned out to be yes. And then we wondered, why did it work? You know, okay, it worked, but why did it work? So we did something that we call interference studies. Frank Glorious kind of renamed it robustness studies. And interference means if you have a reaction that works, how do you stop it working? And when you stop it from working, what did you learn? Okay, that's the key. Something works, you add something, it doesn't work, why? So here's the reaction. This reaction works. This is the second step of our reaction. The CN coupling, catalyzed by palladium with this bulky phosphine ligand, et cetera, and it makes that CN bond. So there's the reaction. It's not complete at this stage at 90%. Now, BINAP is the ligand we used for the rhodium reaction. If we add BINAP, oops, it doesn't work anymore. If we add rhodium, it still works. If we add rhodium and BINAP, it still works, except it's slowed down. And if we double the amount, it slows down more. So what did we learn from that? What we learned was that BINAP will bind and outcompete XPhos for palladium. So the BINAP grabs the palladium, and that's a dead catalyst. In fact, we couldn't call it a catalyst. That's a dead thing, complex. Rhodium does not steal XPhos from palladium. And BINAP and rhodium prefer to bind together because XPhos, it turns out, cannot bind to rhodium. So what we learned at the end was one of the ligands is highly selective for one of the metals, and the other metal takes the leftover ligand. And so we get two reactions going, each in turn. And we did that for the first step and learned more in that same way. Oops. And here's how we use this in a kind of a cute way. If we change the substrate and instead of having an alkyne had an alkene, now when we add the boronic acid, we make a stereocenter. So we wondered what happens if we put a chiral ligand in with an achiral ligand? Will the achiral ligand cause the enantiomeric excess to decrease? And the answer is no. And again, this dying chiral ligand binds only with the rhodium, and the other ligand binds only with the palladium. So we can do asymmetric reactions in the presence of an achiral ligand with no change in the enantiomeric excess. Okay, what I'll do, I think I'll skip this so that I can talk just a couple of minutes about advocacy. So excuse me for that. So this is the group in the summer. These are some of the folks who supported us. This is the lockdown group with everybody in their smiling faces. So I'll just spend the last 8 minutes. So I'm a big fan of saying that scientists shouldn't remain silent. And you know, this is what I spent, let's say, the first 30 years of my career worrying about. How do I get papers in Angewandte, JACS, Nature, Science, whatever it was? But there's another kind of paper that actually more people read than these. I know that is hard for you to imagine. But, you know, there's like 100,000 subscribers to the Globe and Mail, and there's maybe, as my uncle said, 10 people read your paper, but they read every word. So, what about another way in which to get out into the public? So, you know, this was told about me already. This is my background, nothing too interesting there, except, you know, NSERC's been very good to me. So I'm not here to crap on NSERC for sure. They've been very, very good to me, especially industrial support and discovery grants. But something's changed, and those of you who are old enough will know this has changed. We need to think about new faculty and what their hope is and the dreams for the future, and we need to have the people who are the very best in our country somehow be rewarded. And how do we train the next generation, and how do we solve big problems? So this is what you know. These are ways we get funded. NSERC, SHRC, CHR, discovery, partnerships, and so on. This is the facts. For the longest time, of course, discovery is our main source of funding. The success rate is considered high, but it varies within fields. Chemistry has always been more selective than other areas. Big grants, small grants. Engineering tends to be a little smoother across the board. There's these things called CREATE grants, which some of you may know of, training grants. This is a very typical NSERC thing. They're great, except there's no money for supplies. So isn't it great? You can now train 5 more students, except there's no money to pay for all the chemicals they're going to use. So why do we create a program that has no funds to actually support the infrastructure? This doesn't really make sense. And although discovery grants are microscopically analyzed, most of the other NSERC programs are not so microscopically analyzed in terms of funding. There's also something you should know, for those of you who are older, that NSERC used to be called a zero-sum process, a zero-sum game. Everybody whose grant was up for renewal, we poured the money into the pool, and then we redistributed the money from the pool. So the committee knew how much money they had, and they said, we're cutting Lautens 10,000 because we're giving it to this person. And so it was a kind of a horse trade, right? The result was that your career kind of went on this slow uprise to a plateau and then a slow decline. That was kind of the thing. And the committee decided the value of your grant. That was a really key thing. Then in 2000, new model 2000. It's not so new. Most of you, probably some of the students, were barely born then. But they had a bin model. The bin model said, let's put people in bins based on their ratings from exceptional all the way down, and the top bin was triple E. Here was the thing, though. What they didn't say was NSERC and their leadership decided the value of the bin after the fact. So first we're going to put everybody in the bins, and then we're going to decide how much the bins are worth, but not the committee, the bureaucrats. That has some risks because the committee says, well, we think we're giving somebody this much money, but actually NSERC then changes the budget. So in 2015, as you may remember, we had a government elected. We had, for the first time in a long time, a Minister of Science. We had a review panel, which had a number of very significant figures on it: David Naylor, Bob Bergeneau, Martha Piper, Art McDonald. They met, all the things. What did they say? Huge increase in support, 60%, 4% growth in future years. Here was the report posted on the April 10th, blah, blah, blah. You can read this. This would be the plan. Of course, and here's a little bit of information. Here's what happened to discovery grants. If you look, the average size of the award, and as I wrote, the very first time I wrote an opinion, my research grant and my young colleagues' research grant, spread apart by 30 years, were exactly the same dollar value. So just think about that for a minute. Imagine if you were paid what your parents had been paid 30 years ago. That is a pretty depressing statement. So I got mad. So when you get mad, you can do a few things, and I decided if I'm mad, I'll write some things. And I wrote an opinion to the Globe and Mail in 2017, 5 years ago, almost to the day, basically saying that young people are facing too many obstacles. And I won't go through all this, but just say, hey, the most important part isn't patents or products, it's actually training. We don't want multi-generational damage. The government needs to make a major investment. Now, I have to tell you, this was done in parallel with something called Support the Report, which was a groundswell effort by students to pressure the government, who had done nothing. So finally, in 2018, after all this pressure from many, many sources, the government did do something. It sounds like a lot of money, but they said 40%, they only gave 25%. They didn't yet include any more money for scholarships or training. Canada Research Chairs have not changed in value in 25 years. So I started to do some things behind the scenes. I was really upset with some NSERC policy decisions. This was the previous president, not our current one, so no slam against our current president, who's doing, I think, a noble job. So in 1 week, I sent around a letter to 65 chemists, or actually, yes, 65 chemists. And 63 of them signed it in 1 week. Now, to get 65 chemists to agree to anything, never mind in 1 week, is almost unprecedented. And I'll tell you that the people I chose very specifically. I didn't choose a bunch of old guys like me who were well-funded. I chose young people from across the country, from small schools, whose future was on the line, not people whose future was more or less already preset in stone. And what did I ask for? More money for early career researchers, reward the best people, and make our programs all as thorough on adjudication as discovery grants, and add the costs of research, and I requested a meeting with the president. What did I hear? I think the young people call the expression crickets. That means not much. Then I got a letter back, things are in good order, no problems in Ottawa. I tended to disagree with that. So I just spoke to the Minister of Science's Director of Policy. I contacted the Deputy Minister, and I kept writing. We got a meeting with the Deputy Minister. I brought some leading figures and diverse figures from across the country, from UBC, from McGill, some people from industry. We met and we said, hey, we got to break down the barriers between CIHR and within NSERC. More competitions that are open, more about funding the best ideas, not silos and boutique programs. And very few scholarships. We noticed a decreasing percentage of students were getting scholarships, and that was a problem. So I've since starting in 2018, said, hey, graduate students are the lifeblood of our research. They need more money. And I won't go through all the statements. If you really care, you can read them. And then in 2022, I got angry again. Graduate students benefit us while being dramatically underpaid. And then, so university presidents and politicians love to say we punch above our weight. But as it concerns stipends, we are punching in the middle weight class. So that's not our real ambition. And finally, in 2022, just a month or so ago, we need to pay them better. This got a lot of traction, I must say. Getting anything in the Globe gets you a lot of traction. Peaceful protests by students were afoot to say graduate students need to be better funded. The average NSERC Discovery grant, which funds most faculty, is insufficient to cover the stipend of a single postdoc. That's the facts that we are living with, and a serious problem. Significant increases in grants could come with a requirement to pay higher stipends. I believe that path would be met with broad approval. Does anything good come from any of this besides me getting older and angrier? I don't know, and how do we measure if there's no H index for your advocacy, I can tell you. Is there a good way to advocate? I don't know about that either, but the hashtag I invented for myself was educate and advocate, because most of the people actually, when I'm writing an opinion, I'm not writing it really for anybody in this room at all. I don't think any of you will be surprised by a single word that I've said. I'm writing it for the people who are running businesses, for the moms and dads out there who are thinking about their kids going to school. And I'm writing it for the politicians who realize that there's a lot of people who are affected by the decisions that they make. So in writing, you have to write for the audience. And I mean, I don't have to convince you, I don't think. I hope not. But I don't think you can advocate for something unless you inform first. So I can't help but be a professor. It's sort of now in my blood. And I feel obliged to say, here's what you need to know, and here's why you ought to care about it. This was the Support the Report, which was a much broader based, but this shows you the value of social media and coordinated efforts. And I never had been on Twitter in my life until I wrote my first opinion, and then I went on Twitter so that I could find out what people were saying about what I wrote. Because until that moment, there's very little feedback, and I've been told never read the comments section in the Globe and Mail. And that's true, that's mostly wackos. But, they now moderate it, and you can read those comments and not feel the need to explain to your mother why you're a terrible person. So this is, I guess, the end of my story for today. I think this last part is something for all of you, young folks especially, to consider. What can you do? And what's the price of doing nothing? I think we know what the price of doing nothing is. That's basically got us in the place that we are today. But everybody has to find their own way. When you write in public, I can tell you it's quite scary. You're worried about every single word and how somebody will reinterpret your words to mean something different than what you intended. And I did write some pieces about the importance of science in the COVID fight, and I started to get some slightly more off-the-wall replies. And so, it comes with risks, and I don't mean to minimize that. But at the same time, doing nothing doesn't work. And I think if people of my generation and with the good fortune and success that I've had don't speak, I'm not sure that that will, only get an audience if only young people are speaking. So those who are privileged and at the top of the food chain should be yelling as loud as those who want to get there. And so that's what I've done. But, at the end of the day, it's getting to still come to places like this and see happy young faces. And I wrote a piece in the Globe on Monday that was about the importance of actually seeing people face to face. And so if you want something that will make you feel good, I hope, before the holidays, this was meant to be a kind of a sappy, feel-good piece, but actually people liked it. So I'm happy about that. And I thank you very, very much for your attention. I thank you for this honor.
Thank you so much. Just final comments. I couldn't think of a better event today to honor, proud, and getting Valenta. And so please join me again